Welcome back. In this video we will play a bit with scattering matrices. So let's open the tutorial 4. You have different situations where you could be interested in having scattering matrices. So the first scenario could be you want to extract from your network scattering matrices. So for that, you can use the scatter element from the library, and you just put it between the 2 points where you want to extract the scattering matrix. So for example, you can define upstream and downstream. So here it says that I'm listening from this side, and here I'm listening from that side, which means that everything that is between those 2 ears will be lumped in one acoustic scattering matrix. So for example, if I run this section, I am able to build my TX model, and then from the TX model I can use the function plot scattering matrix, and I obtain this body diagram. Let's put it in a format that is easier to see with let's adjust the phases in hertz on a linear scale with absolute value, phase in radians. Here we are. So you obtain your transfer or scattering matrix with your 4 coefficients. Here it's plotted in terms of gain and phase, and you can then determine what is transmitted, what is reflected. So this is the whole scattering matrix of everything that is between your 2 scatter elements. So that is the scattering behavior of all these elements. Now you could want to use it in a different way if you're not interested in measuring between 2 elements. Well, you could just use with one scatter element, and here it's oriented in this way, so it will measure everything that is from the downstream side. So if I extract the scattering matrix from this model, the flame transfer function, the flame, the duct, and the acoustic boundary can all be lumped into the scattering matrix. Let's do that. We can run this scatter2 model and again plot the scattering matrix, again in hertz on a linear scale. Here we have only 2 plots because it is just equivalent to a reflection coefficient. So in this scenario, all the downstream can be replaced by an equivalent reflection coefficient, which is this one. So this is the gain and phase response of the downstream elements. So that is to extract information from your model. Now you could be thinking, what if I want to impose a scattering matrix? For example, I have a complex geometry like a swirler, and I know it will have an impact on my acoustics. I cannot model that in TX, or there is no TX elements that allows me to have a swirler and its acoustic behavior. But what you can do is you want to impose a scattering matrix somewhere in your system, which is exactly that scenario. You have, for example, your simple elements, boundaries, and ducts, and you know that in the middle, for example, you have a swirler with a complex geometry, and you want to be able to capture that with your network model. So you need these scattering elements, and you want to impose the behavior here. So again, it's simply mat file that you need to provide. We'll see in details how to build that. One limitation is that it's an acoustic scattering matrix, which means that between the upstream and downstream, you need to have the same mean values. So how would you do that in practice? For example, you have experimental measurements or CFD simulations where you measured your transfer or you measured your scattering matrix. Here is an example of a swirler. So I have all the measurements in my LNSC data folder. So the acoustic behavior is recovered from LNSC simulations, and we will read the data. And let's run that section. It might take a while. So again, similarly to Flame, as we saw in the previous video, I have discrete data that I obtain from measurements or from experiments or from simulations. Those are the red crosses. And I have my reflection coefficient from upstream to upstream, downstream to downstream, and then what is transmitted from downstream to upstream and what is transmitted from upstream to downstream. And for all these scattering elements or elements of your scattering matrix, you can build a rational fit of your original discrete data. And then there is, sorry for that, in this tutorial, I will let you go in the details of the code. It's very basic. We use the rational fit function for all the coefficients. Then we convert that to state space framework with the TF2SS function. And we also name the input and outputs for better readability. Then there's a procedure to append all the state space matrices into one big state space that model the whole swirler. And then you can build the final state space that represent the whole swirler behavior. For example, in our case, that would be the scattering matrix of the swirler that is correctly appended with the transmission and reflection coefficients. And this swirler or this state space element is the one that you will save into a mat file. So here swirler.mat, and this is what you provide in here. So if you are interested in imposing a scattering behavior in your system, you can follow this tutorial and adapt it to your needs, but the procedure will always be the same. You have discrete data, you do a rational fit to best fit your data points, then you correctly append your matrices, and you obtain a state space representation of your element that you can impose in your TX system. So this is really convenient when you have parts of your system where you know that the acoustic behavior will be important to capture. Then you can afford to do that with high fidelity simulation, extract the acoustic information you need, and impose that in your network model to ensure you will obtain rather accurate results in your low order network approach.